Hello and welcome to Autodesk Simulation TV. My name is Mike Fiedler. For today's topic, Simulation in Action, we're going to be looking at simulation associativity with Inventor. So at the top of this next slide here, I have simulation mechanical and multi-physics noted ahead of simulation associativity with Inventor. So it does fall under the category of both simulation mechanical and multi-physics. Whichever level of simulation you have, this would be applicable to both. And as the rest of the title states, this is the associativity with Inventor. So to be a little more precise in the description, the demonstration is going to look at how we can make changes to our existing CAD geometry within Autodesk Inventor and then quickly produce a new analysis that incorporates those new changes. So I think one of the things that is sometimes confusing to a lot of people whenever they first think of or hear the topic associativity, a lot of times people think about bidirectional associativity. What we're going to take a look at today is the fundamentals or the basics where we're really looking at one direction associativity. I don't necessarily want to change my finite element model and have those adversely affect my CAD model. What we're looking at is as we make changes to that CAD model and I push it back into the simulation, or technically if I turn around here, push it back into the simulation, how do I then execute the new analysis? So some of the key objectives that we're going to do: how to transfer a model from Inventor to simulation mechanical or simulation multi-physics. Not necessarily a primary focus of this particular demonstration, but since we are looking at the CAD part within Inventor, might as well just show you how to get it from Inventor into the simulation. How to run a basic stress analysis using simulation mechanical or simulation multi-physics. We're going to do a linear static stress analysis. And then editing the CAD model and transferring it back to simulation. So we'll make a quick change to it inside Inventor and then get it back into simulation. And then once we have that back into simulation, what do we need to do to set it up, get it ready to analyze again, and then obtain our new results? So if you look in the lower corner here, this is a pretty simple geometry that we're going to work with. Something like a jig. So we have some counterbore holes in each of the corners where you might bolt this down to the foundation, and then we have a couple slots here where we could pin and hold our workpiece or part there onto the jig. So what we're going to look at is, let's say that this jig was configured for a particular part, and then you have some different part you need to make some sort of change to this jig, which I guess wouldn't be ideal, but you know, design changes come along. So once we make those changes to that CAD, how do we get it back into simulation? What do we do with it once we're back in simulation? How much do we need to set up again? So let's start with the model inside the Inventor product. Here I am inside Inventor. Let me rotate the model around for you just a little bit. So there you can see there's our counterbore holes. Having a little bit of difficulty with that word today. And then we have a couple smaller holes in there where the part might be pinned in to help constrain it. So first step, just getting it into simulation. I'm going to choose the Autodesk Simulation tab. And then I'm going to say Launch Active CAD Model. That, of course, is going to pull up my Autodesk Simulation Mechanical or Simulation Multi-Physics. As I do so, it says work points can be imported from the CAD model. In this particular case, I don't necessarily want to do that. The work points will become construction vertices. Whenever you mesh a model, you will get a node from the mesh at the work point, so they can sometimes be useful. In this particular case, I don't need them. The analysis type we're going to do, again, a static stress with linear material models. Of course, you can access the other analysis types there, but again, we're going to choose static stress with linear material models. And we'll have our part inside simulation here in just a moment. Okay, so there is our part. Let me zoom in a little bit here so you can see what we're working with. And what I want to do is mesh this model. And I've already gone ahead and meshed it once or twice, so I have an idea of what size I want to mesh it with. So I'm going to go to Mesh. I'm going to go to 3D Mesh Settings. And I'm going to change the slider a little more towards the fine end of the spectrum. So I could just drag the slider one way or the other. What I'm going to do is go into Options. And I'm going to say that I want to set it to 50%. We'll say OK. And mesh the model. So this is going to do the surface mesh. The solid meshing will come a little bit later. All right. No, I don't need to view the mesh results, though I generally preach that is a good practice just to make sure there's no mesh warnings. Okay, so there you can see our geometry a little bit better. And the element type on the left-hand side has set itself to brick because of my meshing options. I told it was going to be a solid. The element definition sets itself to the most common options there. What I do need to define, because it's red, is the material. So I'm going to choose an A36, and we'll say OK. All right, so looking at this geometry, what I had envisioned is that we're going to hold the piece down by the 4 bolt holes in the corners. So I'll add those constraints on. Now that we're getting to the point in the setup where we're actually looking at loads and constraints on the model, here is one of your considerations. I already know for the purposes of this particular demonstration that we're going to go back to Inventor, we're going to make some change and we want to bring it back in. Ideally, what I would like is to have as many loads and constraints remain on the model after doing so as possible. So there are multiple ways that you can add loads and constraints inside simulation. What I'm going to take advantage of is surface-based constraint and surface-based loads. That way, no matter what change I make within the CAD package, presuming that I have that surface still when I come back into simulation the second time, if that surface still exists, then that load should be reapplied to that surface. One of your load and constraint types that is available is nodal. So I could select this node right here, or maybe hold down my control key and select these 2 nodes or a few different nodes. Those loads and constraints will not remain after you make a change inside Inventor and bring it back. The reason for that is whenever I bring back that new geometry, I have a different volume to it. Whenever it applies the mesh, I'm probably not going to have nodes in the exact same spot. So in this case, one of the considerations, try and use some type of load and constraint applied to something that will remain, whether that is an edge or surface. And again, in this case, we're going to use surface constraints. So I'm just selecting the bottom surfaces of the counter bores there, those 4 surfaces. We'll right-click, add surface general constraints, and I'm going to say fixed. All right. So the next thing is our load. So I'm going to select 2 of the holes here. I'm going to select this corner here, and I'm going to say that corner there. And whatever it is that we have attached to the structure, whether we pin something in or maybe we pin it in and weld it so we can hold our workpiece, whatever the real world scenario is, that ultimately what we're getting is some sort of force out of the plane, or if I move to the side in the Z direction. So we're going to give that a force of, say, 2,500 pounds force. So I'm going to right-click, add surface forces. We're going to make that 2,500 pounds force. And you can see we can make it normal or in some specific direction. We're going to make it the Z direction. And we're going to run the analysis. Remember I said previously it was just doing the surface mesh. So the surface meshing gets kicked off right before it actually executes the analysis. And as soon as the solid mesh is completed, now it'll go into the analysis stage. Okay, so there our analysis is completed. We can see the displacement results here. In this particular case, we're looking at about 0.0006 inches of displacement, so a pretty small displacement on that. If you're wondering about the general dimensions on this, it's 6-inch by 6-inch plate, 1 inch thick. The counter bores are 3/4 inch diameter, halfway through the thickness, and then we have 1/2 inch holes that go all the way through. Then these holes here are about 1/4 inch in diameter, spaced 1 inch apart off of the center line of the model. So there's the displacements on it again, 0.0006. And we can take a look at the von Mises, and there we see 11,782 at a maximum. So here we are with the results of one of our designs. And we look at the results of that design, and based on the displacement and the stresses that we're seeing there, even with a pretty good safety factor applied, you could say that that design is going to be pretty good for a material that yields at 36,000 psi. Now here comes the next thing. Somebody comes along and says, hey, we have some different workpiece, or we want to constrain that workpiece perhaps a little bit differently, so we're going to have to change something up. And you say to yourself, oh man, I already ran this analysis, now I have to do all my work over again. Well, the nice thing about associativity, as I was alluding to a little bit earlier, is presuming that you use the right types of loads and constraints, i.e. surface-based is always a sure bet, then those types of things should be maintained. Let's take a look at it. What we'll do is we'll go back to Inventor here. I'm going to make a change. I'm going to make a pretty simple change. We'll increase the diameter of these holes. Let's say that somebody says, well, instead of the holes that are here, which I believe are 1/4 inch in diameter, what if we make those, say, a 1/2 inch in diameter? We're going to use some bigger pins. So I'm just going to go in and I'll make a change to that sketch. So there's my 1/4 inch dimension. I'm going to change that to a 1/2 inch. We'll say OK. You'll notice that the sketch has been set up so all the other holes will come along for the ride. Let me say finish sketch. All right, so there she is. And again, I'm just going to go ahead and say launch active model, which is the same way we got it into simulation prior. Off the Autodesk Simulation tab, launch active model. There's my work points question that I'll answer no to. Now it's going back to simulation. Now without me touching anything on the model, it's going to come in, it's going to utilize and apply the same exact mesh size that it had before. You can see the material, the element type is still there. If I zoom in over here, the constraints are still there and the loading is still there. So in fact, everything that I had set up prior for my finite element analysis is still there, the same type of loading and so forth. So the only thing that's on me to do in order to take a look at the results of this analysis is to run the simulation. So I'm going to say run simulation. Now of course it did a new surface mesh on my new geometry or revised geometry, so of course it needs to solid mesh that geometry again. But as soon as it solid meshes, it's going to go into the analysis. Just a couple seconds on the analysis here. And there we are. So there's the revised results, getting about 8,650 psi on the stress there. And if I take a look at my displacements, very similar displacements, 0.00064. We should have looked at more significant digits prior. Okay, so hopefully you see how the associativity works in the one direction. It's not too difficult to do, and hopefully is useful for you. One thing I will note, just to point it out, and it will be the topic of a different demonstration. If we go to the Mesh tab, notice that there is a button here labeled Inventor Parameters. So if I go in and click Inventor Parameters, and this will work with Inventor files, of course you can see some of the dimensions here to, for instance, a 6 inch by 6 inch for the part, 3 inch dimensions. So all the dimensions that were used in creating your geometry, you can edit and revise a part that way. A little bit different of a topic, and a good topic for us to discuss in another demonstration. So I'm going to go back into our slides. And in summary, it's quick and it's easy to make alterations to the CAD geometry and obtain new finite element results, nice and quick. Consider the possibility of design changes when you're adding your loads and constraints to the model. So when you're setting up the model, consider the fact that you might need to make some sort of change a little bit later on. Use surface-based loads and constraints whenever possible. Thanks for watching. Have a good day.